Good afternoon, everyone, to the new edition of the Physical Review Journal Club. I am Serena D'Alena. I am a senior editor of PRL, and I will be your host today. We are presenting these exciting letters by the group of Bob Lysak, New Plasma Regime in Jupiter's Auroral Zones, and Professor Ellen Zwiebel will be our moderator today. So before we dig into the exciting physics that have been presented in these letters, I'll just like to give you a very quick update about PRL. As you know, it's the journal of APS and the most cited journal in multidisciplinary physics. We have been the home of many great letters, and some of them during the years have been covered in the scientific background that led to the Nobel Prize in Physics, including the latest Nobel Prize in Physics this year for the discovery of microscopic quantum effect in electronic circuits. We have a journal with a long history, but we'll try always to innovate a bit and evolve. So a quick update from the journal. Last year, we launched Matter, that is basically 2 extra pages of content targeted for the specialists to be added at the end of the letters. This gives the possibility to people to expand on their results when it's needed. And after 1 year, we have more than 30% of letters have been using Matter. Last year, we launched the collection of the year, that it's like where we gather our best letters across all areas of physics that we covered. It's been very exciting effort, I'd say. This is an editor-driven collection, and we're working on the one for next year, but please take a look at this one. And last but not least, we launched Forward-Looking.
All right, we'll talk to you later.
Scott, you're
okay. Bye.
Okay, and PRL forward-looking essays are invited pieces to welcome work from areas across the physical science, but most importantly, to inspire the new generation of physicists of what's nice, exciting, and ready to be discovered in the next few years. So with that said, I'll stop sharing the screen and I'll leave the floor to Ellen. Ellen Zwiebel is the William Professor of Astronomy and Physics at the University of Wisconsin-Madison, and she is our moderator for today. Thank you, Ellen.
Hi, can everyone hear me? So yeah, I'm Ellen Zwiebel. I have known Bob Lysak since he was either a grad student or a postdoc at Berkeley working with Mary Hudson. And he was immediately snapped up by the University of Minnesota to be a faculty member, where he's been ever since. He really puts the plasma in space plasmas. I'm very excited to hear his talk because, as I think we'll see, this could have really wide-ranging application even beyond Jupiter. So Bob is okay with questions during the talk. I guess I would say the same thing that I do in thesis defense. This will be a pretty short talk. There'll be lots of opportunity to ask questions. So only if there's a piece of jargon or something where you absolutely cannot go on without asking your question, then do so. Please do so. But otherwise, we have plenty of time to talk. This is a journal club. So Bob, please take it away.
All right, thanks, Ellen. Yeah, I think I was a graduate student at the time. It was a meeting in San Diego, I believe. So it was very nice. Anyway, let me share the screen and we'll get started with the talk. Oops, of course it starts in the middle. All right, let's get into the mode. All right, can you see the screen very well?
Yes.
All right, let's see, and let me get rid of the controls. All right, so this is some work that was inspired by operations of the Juno satellite, which is in polar orbit around Jupiter at this point. And my colleagues, Ali and Sadie and Bill, are involved with the WAVES experiment on this, which is measuring plasma waves in the environment of Jupiter, and particularly in the auroral zones, which is the part that I'm most interested in. And the one major discovery that we've found here that inspired the paper is it turns out that in Jupiter's polar regions, the density is extremely low, and below 1 particle per cubic centimeter. But the magnetic fields are very strong, greater than a few Gauss. And this leads to the condition that the electron plasma frequency is less than the ion cyclotron frequency. You know, when we teach plasma physics classes, we always say that the electron frequencies are all way higher than the ion frequencies, and often treat them separately. The ion frequencies and treat them separately. Excuse me. Yeah. Anyway, it turns out that in this regime, there's a new structure to the plasma waves that we'll talk about here. I'm getting some crosstalk here, but we can.
I'm sorry, MBA Michael, could you mute yourself?
There we go. Okay, anyway, I realize that probably most people here are not familiar with the aurora or with Jupiter. Actually, I hope that everybody saw the aurora in the last couple of days. That was one of the best storms ever a couple of days ago on Veterans Day. But there's some differences between Earth and Jupiter shown here. And the left-hand picture is a picture from the VIS satellite from Lou Frank of the University of Iowa, which was actually an older picture taken, I don't know, something like 30 years ago. And on the right is a rather famous picture from the Hubble Space Telescope by John Clark. Not the John Clark that just won the Nobel Prize, but a guy who's done a lot of great imaging. And we point out a number of big differences. I mean, at Earth, the currents that give to the aurora are driven mainly by the interaction of the Earth's magnetosphere with the solar wind, whereas Jupiter is quite different. Jupiter is a rapidly rotating planet, and its magnetospheric dynamics is largely controlled by that co-rotation. And in fact, this a band here, I don't know if you can you see my mouse going through it? Yeah, okay, good. This band here that's going around is the point where co-rotation begins to break down. And at that point, the magnetic field gets sheared, which gives rise to field-aligned currents that map into the auroral zone. And so that sort of part does not show up at Earth in that same way. The other thing that's very different about Jupiter is it has moons very much inside the magnetosphere. Right here is the footprint of the moon Io, the volcanic moon that blows off all the gases into the magnetosphere. And you also see Ganymede and Europa. And some people say they can see Callisto in here, but Callisto gets messed up with the main auroral stuff. The other big thing is that on Earth we have discovered over many years now that there's basically two modes of acceleration of electrons to make the aurora. In some cases, there's basically a potential drop, something we call a plasma double layer, that can accelerate all of the electrons to the same energy. And in fact, the evidence for this is also that we see the ions, mostly hydrogen and some oxygen ions, going upward at the same energies. So it's very indicative of a parallel potential drop. But on the other hand, some of the observations show a very broadband spectrum of electrons, where there's many broad energy range. But at Earth, the monoenergetic part is dominant. Both of these same type of acceleration mechanisms are operating at Jupiter, but Jupiter seems to be dominated by the broadband acceleration, and this broadband acceleration. Well, there's a few possible explanations for this, but my favorite explanation is that this is acceleration of the electrons in what we call kinetic Alfvén waves, which is a very important topic in many areas of plasma physics. One thing about this broadband acceleration is it's bidirectional. So even in the regions where the overall current is downward, which means that electrons are moving away from the planet, at Earth, that's generally a dark region. no auroras. In fact, sometimes it's called the black aurora region if that occurs within the diffuse aurora. But at Jupiter, we see bright aurora even in the downward current region, and it's due to this broadband, presumably Alfvénic acceleration. Then moving to what we really are talking about here is that on Jupiter, we also see this polar emission. Sometimes it's called swirl because it's very time dynamic. And that is very rare at Earth to see any sort of aurora in the polar regions. As you can see in this particular picture, the polar regions themselves are very dark. And so this is a big difference between those planets. And again, in addition to these moons. Okay, so I'll say a few things about Juno, which has enabled these missions. Juno was put into orbit around Jupiter in 2016, I believe it was, and has been orbiting in a polar orbit around Jupiter ever since. It's the first satellite we've put into a polar orbit. Other satellites like Galileo, of course, the Voyagers just made, and Cassini just made flybys of Jupiter, but Galileo was in an equatorial orbit. This is in a polar orbit that goes over the poles of Jupiter, and so we can measure these auroral emissions. And as you go in this diagram, as you go into these as these orbits come closer and closer, this constitutes what's called the extended mission for Jupiter. The prime mission was only the first 33 orbits or so. The orbits are labeled in Jupiter by PJ, which means perigove, right? Which is the Jupiter-oriented term for the closest approach. But the one thing that's important for our purposes here is that, as you can see, as the mission has evolved, we're getting all of these very low altitude passes over the polar cap of Jupiter, and that's enabled some of the observations that we're going to see here. So over here is sort of the usual picture of the various instruments on Juno. The one that we're going to focus on here is the WAVES instrument, which is the one which, of course, has measured these particular types of waves that we're going to talk about. Of course, another big story about this is that the extended mission of Juno coincidentally ended on September 30th, which is an important date, of course, in the politics of this country. And there's been a second extended mission proposed, but of course, because of the government shutdown, nothing has been decided about that yet. But we're hoping that the mission will continue, which will give even better observations over the polar cap. Okay, so now I'd like to throw this over to my colleague Ali Suleiman, who will talk a little bit about how we use wave measurements to measure plasma density.
Hi, everyone. I'm Ali. So as Bob mentioned, we routinely find very, very low densities of plasma above Jupiter's polar cap and the auroral zones. So the way we make these measurements is we use the plasma wave instrument, which measures high-frequency electric and magnetic field. And with that instrument, we can identify a number of wave modes. And the relevant wave mode for this exercise is the ordinary mode, which is a transverse wave that has a lower frequency cutoff at the electron plasma frequency. So when we look at the spectrogram and we see the ordinary mode wave, we can see a distinct low frequency cutoff, which we digitize and use that to directly compute the electron density. It's particularly useful in regions of very low densities because it remains present. Otherwise, using a plasma instrument, which counts the number of particles per volume, once you get to around 0.01 per cc, that becomes very challenging. And also above the auroral zones, there are issues with low signal to noise ratio. So at these extremely tenuous regimes of low plasma densities, we heavily rely on plasma wave observations. So to give you a flavor of what these numbers look like in the auroral zones, you can see the figure that's labeled C in the top right. So the arrows label the data points that were returned by the wave instrument. And what we're looking at is Juno passing above the auroral zones in the southern hemisphere, going up in latitude. And you can see that as we approach the main auroral emission, so that's the region where sort of the purple band is Z1, that is zone 1, that's the region of upward field line currents. You can see that the densities go down quite dramatically to the order of 10 to the minus 2 per cc. And then the figure at the bottom is a statistical picture of the densities above the auroral regions. And you can see in the above panel A, that just gives you the absolute electron density. The x-axis is just how many degrees we are away from the main auroral emission. So negative numbers are just equatorward and positive numbers are poleward. And it very clearly shows a trend that the more poleward we move, the lower the densities are. There's some extreme cases where the densities go down to about 10 to the minus 3 per cc. And the very bottom panel shows how this compares to the magnetic field. So it's the ratio of the electron plasma frequency to the electron cyclotron frequency. And not only this is consistently less than 1, which indicates a very underdense or very overmagnetized plasma, but there are also occasions where, as Bob mentioned earlier, that the electron plasma frequency is lower than the ion cyclotron frequency, which is indicated by the red dashed line. So this is really unique in the context of solar system observations, whether at Earth or Saturn, the solar wind, or even the near sun environment as well. Bob, you can move to the next slide. I'll speak to the figure on the left, so the top panel. That's, again, just to give you a flavor of what these measurements look like from the plasma wave instrument. These are electric field measurements, and what we're seeing is a frequency time spectrogram. And those are the waves, the ones that are lit up in sort of yellow-orange are the waves that Bob will talk about in detail. But essentially, these waves have an upper frequency cutoff at the electron plasma frequency. And those are sort of shown in the solid black line. And you can see that those are far lower than the white line above, which is the ion cyclotron frequency. And the panel below is just the digitized density from those measurements in the spectrogram. Bob, I'll turn it over to you now.
Okay, well, so inspired by these measurements, then we started to say, well, let's start at the beginning and go back to the cold plasma dispersion relation, the same relation out of sticks that those of you that teach plasma physics are probably well familiar with. And but of course, what's unusual about it is that usually you plot these things in regimes where the electron plasma frequency and the electron cyclotron frequency are comparable. But this is the case. In this case, we just did the same dispersion relation, which still holds for these very low density plasmas. At this lower density, in fact, even at considerably higher density, the Alfvén speed becomes essentially the speed of light. It gets saturated at that point. Obviously, can't go faster than that because of relativity and all that. So the Alfvén wave is basically in that solid black line where it says omega equals kc. But if you go to wave normal angles, the angle of the wave vector with respect to the background magnetic field, and it becomes more oblique, as you can see, what's starting off as this Alfvén wave is going off into this regime, and you'll notice that at each different angle, this is a function of the wave number normalized to the speed of light divided by the ion cyclotron frequency. At each angle, the frequency becomes a constant, and this is what we call a resonance cone. And usually we observe this in the Whistler band above the ion cyclotron frequency. So this is another unusual aspect of this case. And it turns out that this frequency, I didn't put it on this slide, but this frequency is basically the plasma frequency times the cosine of this angle. So this is kind of the standard form of a dispersion relation that, as I say, those of you that teach plasma physics class, if you're looking for an interesting problem to give your students, even a graduate student should be, maybe even an undergraduate student taking a plasma physics course should be able to reproduce this kind of a figure. So the new thing in this thing is not necessarily the theory, but the observations. But we have a different way of plotting this sort of thing. We're promoting the idea or proposing the idea that this wave is excited at the Landau resonance by electron beams, which we observe in this region. And so in the left-hand figure here, we have a plot. It's the same dispersion relation as before, but now it's plotted as a function of perpendicular wavelength and frequency, and each line corresponds to a parallel phase velocity associated with electrons of the indicated energy from 1 10 100 keV and then 1 MeV. So you get this different picture of where the Landau resonances should occur. And so this is the case where this will build up to the kinetic theory that I'll talk about in a little bit. But this gives us a new way of looking at this. Notice that maybe if I go back up here, this regime up here, which is this O mode that Ali talked about here, these waves all have phase velocities greater than the speed of light. So they do not have Landau resonances, and their excitation depends on cyclotron resonances or other processes. The other thing that's interesting about this and important for particle acceleration is that, of course, in your usual statement about plasma physics, and certainly in the MHD approximation, you say, well, the parallel electric field is 0 in a collisionless plasma, but that's not true for these waves when the wave number becomes as large as it is here, and we start to develop a parallel electric field. And the plot here, and it's the same 4 curves for 1 10 100 and 1000 keV. It shows the ratio of the parallel to the perpendicular electric field, and you can see as you go up towards the plasma frequency here, this is the range here is at the plasma frequency. The field becomes more and more parallel, and so that can give rise to this acceleration. And in fact, it's a wave field, so this is what we think is one of the mechanisms causing this broadband acceleration of the electrons. The solid curve here, you notice that I just have less than 100 keV here. In the lower energy cases, all of these curves converge into what we call a resonance cone. And then I'm going to throw this all over to another one of our co-authors, Sadie Elliott, who is a senior researcher at the University of Minnesota.
Hi, everyone. I'm Sadie. So I get to talk about the interesting shape of this emission that we see on a frequency time spectrogram, which we have called a saucer or a funnel-shaped emission. So the plot on the left side here is basically showing you the group velocity angle. So that's on the y-axis, which is the Poynting flux angle relative to the background magnetic field as a function of frequency. And it's showing these curves for varying energies of electrons that are in Landau resonance with the waves. So you can see that the energies go from 1 up to 1000 keV, with 1 being the line that kind of overlaps with the solid curve here. So the solid black line, which is the solid black line is showing you the resonance cone angle. So this is where the index of refraction is going to infinity. And that basically is indicating a maximum angle with respect to the magnetic field for the waves. So we can see that lower energies basically follow that resonance cone angle, and then the larger energies are more parallel to the background magnetic field. And so how this kind of manifests itself on a frequency time spectrogram, which is what we're observing from the waves instrument. Sorry, I'm getting some background. Okay. How that manifests itself is it looks like this saucer-shaped emission. So the reason why we get this emission shape is due to the spacecraft passing through a source field line for these waves. So it will see the higher frequencies first on the left-hand side of the funnel, and then it will see the lower frequencies later in time. And that's shown kind of by the left figure, which is showing you, as frequency is increasing, that angle changes substantially. And so then the alternate would be true for the other half of the funnel. So that's kind of why we see this saucer or funnel-shaped emission on a frequency time spectrogram. And that's shown, an actual observation of these waves is shown in the bottom right figure here. And also, I wanted to note that an important thing that we can also do from these observations is we can actually track them back to their source region. So we could actually calculate out what that DE distance is, which is shown in the kind of cartoon at the top. by using this kind of dispersive nature of these waves and tracking that upper cutoff, which is the plasma frequency. So this saucer-shaped emission it might be familiar to you because these have been observed commonly. They're called VLF saucers at Earth. However, these are in a different plasma regime. So those ones at Earth typically propagate in the Whistler mode branch, whereas these ones are this new plasma regime that Bob is going into detail about. So I think that's what I have to say. Thank you.
Okay, thanks, Sadie. Okay, so we're talking here about excitation of these waves at the Landau resonance, and of course in the fluid theory that we've been talking about so far, of course we don't see these Landau resonances showing up, so we have to go through kinetic theory, and a while back actually we did some modification or simplification of the fully kinetic plasma dispersion relation, which is applicable for frequencies below the ion cyclotron frequency and for larger K-perp. And this has the advantage that for the plasma physicists in the audience, that it basically decouples the shear Alfvén wave from the fast mode wave, and so it basically takes the usual 3x3 dispersion relation and reduces it to a 2x2, which is considerably easier to deal with. And so it takes this very simple sort of form. Well, at least it looks simple, but of course this coefficient here, this factor G, includes finite ion gyroradius effects, and the factor P includes the plasma dispersion function. So this is the part that depends on the where the Landau resonances show up. And of course, then this whole dispersion relation we have to solve numerically because this quantity that I've written as psi here is the ratio of the parallel phase velocity of the wave to the electron thermal speed, which of course depends on the frequency as well. And so we iterate this relationship in order to calculate the frequency as a function of K parallel and K perp, which these plots show, with K perp being the horizontal axis and K parallel being the vertical, normalized to C over omega PE, the so-called electron inertial length, or sometimes referred to as the collisionless skin depth. Like I said, I like to tell my students everything in a plasma has at least 3 different names if it's worth anything. So we have to learn all of them. And this is for looking at a black background plasmas in the panel A at 10 electron volts, where we basically reproduce the cold plasma dispersion relation. Notice that these lines of constant frequency just radiate outward. This is indicative of the resonance cone type of structures that we've been talking about. But when you talk about more realistic cases where the temperature is sort of the order of a kilovolt, and it's a difficult measure to make at Juno because of the again, the scarcity of the amount of plasma that Ali mentioned earlier. But you can see that there's a different shape to the dispersion where the curves start to turn over. And it's perhaps easier to see in the next slide where we plot this in terms of a line plot. And again, in the cold plasma case, here's for the different values of K perp, we go up to the plasma frequency and it saturates. But then as you go to higher and higher temperatures, you start to see that things start to rise above the plasma frequency to some extent. And that's very indicative of the structure of Langmuir waves. You know, in Langmuir waves, when the wave vector becomes the wave vector times the Debye length becomes the order of 1, then the plasma wave shows dispersion. So we have this case where in fact the slopes of these curves are comparable with the electron thermal speed in the plasma. So these give us the background kinetic dispersion in this problem. Now, if of course the other thing that we have, if we don't include a beam in our dispersion relationship, then the wave is damped, and the blue colors here indicate the damping. And you can see as we go off, and again this is K parallel versus K perp, as we go into the higher values of K-perp, you can see these waves become damped. In fact, we had a little bit of concern going back here. Now you're saying, well, these things are going above the dispersion, above the plasma frequency. How can we still see the cutoff? And I think the answer to that is that those waves are the ones here that are being damped by lambda damping on the background plasma. So that kind of squelches those very high K-perp modes. Of course, the damping here is still relatively weak, but it nevertheless is present. And just to show some of the data as well, here again is some electric field data, and here's some of the plasma data that we're running from here. And here you see there's these broad spectrum. This is the electron energy spectrum going up, in this case, from about 40 keV to 500 keV. This is from what's called the JEDI instrument, which is the Juno Energetic Particle Detector Instrument, I think is the acronym. And so you can see that we're talking here about hundreds of keV electrons present here. Of course, again, at very low numbers. That doesn't invalidate the low densities that we're seeing, but we do see these cases. And you notice here's the pitch angle with 0 degrees in the northern hemisphere of Jupiter, meaning upward. Jupiter's magnetic field is reversed from the Earth's, by the way. The magnetic field points south or upward in the northern polar regions. So this is sort of particles that we're thinking about here. So if I start putting in a particle beam into the dispersion relation, then we start getting acceleration or excitation of the waves. And so this is some plots showing that aspect of things. And these shapes may look a little bit reminiscent of what you've seen before. Of course, these follow those Landau resonance curves that we showed in the earlier slide. And so you can see that we get, this is again plotted versus K-perp, and in this case K-perp and KZ. It's the same data. This is K-perp versus KZ, Z being the parallel direction. And here it's K-perp versus omega. And the important thing to note here is that the dominant growth rates in these cases are up around the plasma frequency. There's some noise in here due to actually the multi-valuedness of the dispersion relation at this point. So there's a little bit of a mess there. But this is the sort of wave excitation that we see from these kind of beams. And here's another example, looking again at a plasma with a background temperature of 1 kilovolt with 100 keV input on it. And again, we see these curves of maximum growth being following those Landau resonance curves that we calculated from the cold dispersion relation, and again with damping at frequencies above the ion cyclotron frequency. So we have a nice little story here of these various waves that can occur in this region. So the real question that all of this raises is, why are these plasma densities so low? I mean, we don't see such low densities at Earth, for example. One reason that may be true is that at Earth we have, in the polar regions, is a mixture. The ionosphere is a mix of hydrogen and oxygen. The so-called ambipolar potential, which holds electrons down to the ion scale height in order to maintain quasi-neutrality, is basically governed by the oxygen ions, and the hydrogen ions are free to flow outward, which is what we call the polar wind. But Jupiter's ionosphere is mainly hydrogen. In fact, the main minor ion in this ionosphere is H3+, which is a strange ion that you have to think about for a second. But anyway, that may be one basic reason why these densities are so low. But another consequence of the low density is that one of the things that people in the auroral zone physics have been talking about for quite some time is that parallel electric fields in plasmas tend to occur in regions where the density, basically the ratio of the density over the magnetic field strength, is low. And the reason for that, a basic reason for that, is that is that the current density in a converging magnetic field structure is proportional to B, but the current density is the density times the velocity times the charge. And so if the density is low and B is large, that means the velocity of the current carrying electrons has to be large. And if that velocity that's required is greater than the electron thermal speed, then simulations of double layers that have been done over the last few decades have suggested that's where these double layers can form, where kilovolt or multi-kilovolt potential drops can form over relatively small distances. And in fact, we see these sort of things in the polar cap. This is a little bit beyond what we had in our paper, but another very strange observation in this case is that we see heavy ions, sulfur and oxygen, with energies of over 1 million volts, MeV, precipitating in this region. And of course, it is a downward current region, but those ions are the sort of ions that are produced in those volcanoes of Io. So presumably those have been emitted at Io, of course, as sulfur dioxide mostly. It becomes dissociated and ionized. Those propagate outward under the influence of these centrifugal forces. There's, of course, a turbulence in this plasma sheet. And somehow or another, and that's what we're trying to work on in the future, is those ions get accelerated back towards Jupiter and perhaps is responsible for making that swirl type of case. So this is the sort of story that we're thinking about. And there's a lot of interesting physics still to be done here. One thing that a group at Kansas, this guy Houston and all have worked on is what happens if an oxygen or a sulfur ion at a million volts hits the ionosphere. It's probably going to splatter up some electrons, and that may be the source of these upward going hundreds of kilovolt electron beams that we're seeing. So this is kind of the story that we wanted to say. And I think I just have one slide, which is a photo that I took 2 nights ago from South Minneapolis. So I hope you all were able to see the aurora at that point. So that's basically our presentation. So we're ready to take some questions.
Well, thank you, Bob. I see a lot of hands going up. So maybe I'll take the prerogative, moderator's prerogative, and ask you the first question, which was, what surprised you the most about doing this research project?
Well, I think the thing that really is a surprise is just seeing the plasma in this extreme state. I mean, that's something that we have not observed anywhere else. I know we've been to every planet, and including planets that aren't planets anymore, like Pluto, and haven't seen this sort of region. Now, of course, at the outer planets like Uranus and Neptune, we haven't had an orbiter like this that's been able to observe such structures. So seeing the observational side of things is the most surprising thing. As I mentioned, the plasma physics, the theory behind it is actually quite basic in this case. It's just the standard sorts of dispersion relations that we all know and love. But applying it into this different parameter regime is really the surprising point.
Okay, well, I actually don't see any other questions, so I'm going to keep going. So you mentioned possible applications to other objects, exoplanets and stars, and one way of making the electron plasma frequency very low is to make the electrons very heavy, which you can do if they're relativistic. So I think at that meeting where I met you, Alex Dessler gave a talk about how Jupiter is really just like a pulsar. So I wonder if you've thought about applying any of this work to relativistic plasmas.
That's a real good question.
Or pair plasmas.
Yeah, well, like I always say, pair plasmas, electron-positron plasmas are a simulator's dream because the mass ratio is unity. So Of course, one of the problems with plasma simulations is the large mass ratio. Yeah, the analogy to pulsars has been made before. Of course, again, Jupiter doesn't make antimatter, at least as far as we know in this case, so it's not quite at that extreme yet. But yeah, certainly pulsar magnetospheres are an interesting topic that way, and of course, much more extreme values of the magnetic field strains here. Here we're talking a few Gauss instead of what 10 to the 12th or something like that. So those sorts of things. So pulsars, I think, are a little bit different. Now, I mean, we also obviously have a growing library of exoplanets that we know about, many of which are Jupiters or super Jupiters, sometimes referred to, and presumably some of those planets have magnetic fields as well. And of course, I should mention these waves that we're seeing are not free space waves. These are waves that are confined within the plasma. But those O-mode waves we were talking about, those are waves that can propagate out to free space. And it's very likely that our first real indication that an exoplanet, for example, has a magnetic field is going to be due to observing the radio emissions that it produces.
Okay.
So it's of course it is kind of a trendy thing right now. Exoplanets are kind of cool, and we're moving from a phase of just knowing that they're there to trying to figure out their properties. And of course, my colleagues in the astronomy department are very interested in making those sorts of observations.
Okay, thanks. So we have a question from, so I apologize in advance if I don't pronounce this name correctly, Abdul Ghaffar.
Yeah.
Is that right?
Yes. Yeah. So can you hear me?
Yes.
Yes.
Yeah. If you don't mind, can you move to the slide where the expression of Alfvén wave at the denominator?
Which?
Yeah, that's right. Yeah.
This one?
Yeah, this one. So is there any, because as it is a fantastic tool, all the Bob and Ali and Sadi, just I'm wondering about the role of neutral in it, because electron density is very less. So it just kept me some exciting questions. What about the presence of neutral? If neutral would have been there, they might couple with the wire collisions with and they too magnetized. So there is a neutral dynamics may come into picture. Of course, it is very infancy stage, but I work on a neutral dynamics and is it the fully ionized plasma or partially ionized plasma or weakly ionized plasmas?
Well, it's perhaps not fully ionized, but at these are at altitudes of something. We like measuring things in terms of Jupiter's radius. These are at altitudes of something like half of Jupiter's radius above the planet, which about 30,000 kilometers. Jupiter's radius is about 70,000 kilometers. Now, when we get so at this altitude, there may be still some neutrals there, but the neutral ion collision frequencies are negligible, so we don't have to worry that. But when you get closer to the planet, into the ionosphere, and in fact, that's really one way to define where the ionosphere ends and the magnetosphere begins, is where the collisions become important. And in that case, the collisions will be important and in fact give rise to what we call Hall and Pedersen conductivities that actually close the field of line currents that we're observing at Jupiter. So again, Jupiter's ionosphere is unique as well because it's actually got a similar density and temperature to Earth. The peak densities are about 10 to the 5 per cubic centimeter, peak plasma density, and the temperature is about 1,000 Kelvin. But it's whereas Earth's ionosphere is largely oxygen and nitrogen, obviously, since the atmosphere is that way. Jupiter, of course, is a big ball of hydrogen. So the ionosphere is primarily hydrogen. So the chemical composition is quite different. And as I mentioned, these precipitating ions are when they come down, and they're going to interact with both the neutrals and with the plasma, and we know this at Earth, that when the auroral electrons hit the Earth, they backscatter electrons up, which actually help to form the double layers that we think are accelerating the particles. So the neutral dynamics are important in the ionosphere. You know, in the first few thousand kilometers above the surface, well, above what we call the 1 bar radius of Jupiter. You know, Jupiter is a ball of gas. So what's the radius of Jupiter? If you're looking at it with a telescope, you can see that very easily. But when you're down in there making measurements, you have to define it. And it turns out that the location where the pressure is equal to the Earth's atmospheric pressure is about where we put that's what we define now as the radius of Jupiter, which is, like I said, about 70,000 kilometers. The interaction between the plasma and the neutrals is of course very, very intriguing in all of these cases.
Thanks.
Thank
Serena,
you very much, Bob. Thank you very much.
Do you have a question, Serena?
Yeah, just a quick one and almost a follow-up, but I really love this result because it had a little piece to something that it's very common to any plasma physicist, the decay-log diagram. So that to me was very neat. It's like classical textbook addition. So congratulations. And for me, it's like, okay, very naively, you talk about ion composition, and then we know the strong rotation in the Jupiter atmosphere. Maybe this plasma density indicates gives some hints on the possible planetary formation mechanism, maybe somehow related to, because Jupiter is very big and a strong rotation, almost being another star with the sun. So could you perhaps have some hint on like the staging in life of a planet or its formation, if so?
Yeah, that's not really my particular area of interest. I'm not quite sure where, how all that accretion starts to take place. I mean, of course, we know that Jupiter probably, from what I've heard about this, and again, it's not my specialty, that Jupiter formed relatively early in the solar system, and in fact, I think in the words of Fred Bagenal, acts like a big bully that's pushing the other planets around and perhaps preventing the asteroids from coalescing into a planet. And there's a lot of other speculation about what's happening in the formation of the solar system. But it's a fascinating topic, and it's in fact worth a lot of combined investigation. In fact, one thing that we're contemplating in Minnesota is to work more into a joint planetary program, because we have also a Earth Environmental Science department that is also interested in planetary science. So it's a subject for future work for sure. But I can't give you any great answers right yet.
Thank you. Thanks a lot.
Well, I don't have an answer, but this is sort of a comment and a question. I thought that the Eoplasmatorus was a very important source of particles, and that is sort of special. So I don't know what role you think that plays in the aurora or the composition, mass balance.
Oh yeah, no, that's a very good thing. Well, in fact, if I go back to the beginning, again, this little spot in the aurora here is on the magnetic footprint of Io, and as Io moves through the magnetosphere, or more precisely, as the magnetosphere moves past Io, because the co-rotation period of Jupiter is 10 hours, and Io's orbital period is a few days, if I remember correctly. So it's really the plasma passing past Io that actually generates Alfvén waves. Ali and I have written a paper on this as well, and produces, and Alfvén waves. The other thing that's formed is when Io emits all of these gases, and those gases are basically spun out into this what's called a plasma disk of, again, largely sulfur and oxygen ions. That actually is of course, that's a very high density plasma, and the plasma in between that and Jupiter ends up being very low. In fact, the Alfvén speed is close to the speed of light, pretty much in all of that case. So waves can actually so the Alfvén waves can bounce back and forth between the ionosphere of Jupiter and this plasma torus that goes around, that's produced by the iogenic plasma. And that bouncing, if you look, and Juno has made measurements like this, if you look at this tail in very close, and then particularly in the infrared, it's actually not just a smooth tail, it's a series of spots. And we think that's where the Alfvén waves are bouncing up and down, and when those currents hit the ionosphere, it produces a bright spot. Of course, from afar, this is a Hubble Space Telescope picture, that those all kind of smear together. But when you take a picture of it from the Juno satellite itself, then you can see all that structure. So those are the torus is a major source of plasma in the magnetosphere, but as I mentioned, we observe energetic heavy ions, sulfur and oxygen ions, coming in at MeV energies in this polar region, and how they get there is something that we're working on.
Thanks. So, yeah, so your solutions of the linear dispersion relation are certainly very illuminating. Do you have any plans to investigate the nonlinear behavior of this system and see what determines the final amplitude or saturation of the?
Yeah, of course. We basically, the linear dispersion relation tells you the waves should exist, but doesn't give you the more quantitative information that you're talking about. Our suspicion is that basically, if I go back to this figure here of the electron density or electron observations, of course you see this sort of smearing out thing, and where maybe you can see there's a little bit of a brighter red here near the top of this. It looks very much to me like there's a quasi-linear diffusion process happening, and maybe this is like a quasi-linear plateau. I think, if I remember correctly, Ellen, you've worked on this sort of thing before, and so I think there's a possibility that the ultimate mechanism is that the beam kind of gets smeared out by quasi-linear diffusion. And there's another observation that we're working on right now, where we have an inverted V type of electron distribution, where it goes up to a peak energy and then becomes lower. And near the peak of that energy, the spectrum becomes broadband, which looks very much like it could be that. And so one approach that we're using to study this is by using test particle simulations in our fluid codes to model that. But of course, there's always these problems of scale. Is that self-consistent plasma particle and cell type simulations or glasshouse simulations? It's hard to make them very big in terms of spatial scale, and getting the overall global structure of the field lines is difficult to deal with. So there's a lot of challenges going on with that, but I think that's an avenue that we are probably going to pursue.
Great. Does anyone else have a question or a comment? I see applause, which I too applaud. Okay. So I want to thank you, Bob, and I want to thank all the co-authors. This was really interesting, and yeah, why don't we say goodbye?
Thank you,
right.
everybody, for attending too.
Thank you.
And thanks for your interest in this research.